Okay, very good afternoon. So we are in unit number 2. So problem solving through search. We have seen different types of search techniques. So we have seen uniform search techniques, ununiform search techniques. Then we have also seen heuristic search techniques, stochastic search techniques. And after seeing all this, we are actually seeing what kind of AI or what kind of search techniques have been used in the game playing. So alpha beta pruning and the first one as a minimax, these 2 points comes under game playing, and we are going to see how these algorithms are used as far as the game playing is concerned. So obviously they are the part of AI. So whatever the algorithm we are going to implement for games, obviously AI is having that kind of role. So that role is been played through the algorithms. So out of which we started the first algorithm, which is called as minimax algorithm. So I just started it. We'll again go back. So we'll have some revision of the first slide and then we'll move on to the actual working of this minimax algorithm. So as we know that minimax algorithm is a recursive algorithm, which is also called as a backtracking algorithm. So that is used in decision making and game theory, and it gives an optimum results. So it can provide you the optimal move of the player for the player, assuming that the opponent is also playing optimally. So the result will come as soon as I am playing game with the computer. So I'm expecting the computer to play optimally. The computer might be thinking then the opponent like me is playing optimally. So this is how the game goes on. It is a recursive algorithm. It is mostly used for game playing in AI. So these types of which kinds of games in which this minimax algorithm is implemented, like chess, checkers, tic-tac-toe, and various two-player games. So wherever there are two-player games, at that time, we are going to use this minimax algorithm. The algorithm computes the minimax decision for the current state. In this algorithm, two players play the game. One is called as max and the other is called as minimum. So why the name to this algorithm is given as a minimax algorithm? Because here it is, the game is related with two players. So all those games which are related with the two-player games, they are implemented through an algorithm called as minimax algorithm. So obviously one of the opponent will be max and the other opponent will be minimum. Both the players fight it out as opponent players gets the maximum benefit when they get the max, while they get the maximum benefit. So obviously if I am designing a game, I will be getting mostly benefit and the opponent will get the less benefit. So the opponent players will have a minimum benefit and the player which is actually main player will have the maximum benefit. So the game is designed in such a way. Both the players of the game are opponents to each other, where max will be selected, where max will select the maximized value and minimum will select the minimum value. So obviously both the players are opponents to each other. So in that case, if the max will be, max means the opponent, one of the opponent. So if it will play, then it will select the maximum value. If the other opponents will play, then it will select the minimum value. So in this way, the game plays. So one is max, the other one is minimum. The minimax algorithm performs a depth first search algorithm for the exploration of a complete game tree. So it is like a tree. It's a game tree. So you need to have that search technique. So which kind of search technique is mostly used here is a depth first search algorithm, that is called as DFS. The minimax algorithm proceeds all the way down to the terminal node of the tree and then backtrack the tree as a recursion. It will go from top to end, and then from the end it will again backtrack, and henceforth it is called as the recursion because it goes from the backtrack to the top, from top to bottom and from bottom to again back to the top. So that is backtracking takes place, and because of that, this algorithm is also called as recursive algorithm. Now, how the working takes place, working of Minimax algorithm. The working of this algorithm can be easily described with the help of an example. So let us assume that there is a game tree, and always obviously having two-player game. It's a two-player game. The two players, one is called as maximizer, the other is called as a minimizer. Already we have seen this. So maximizer will try to get the maximum possible score, whereas the minimizer will get the minimum possible score. So in this way, it is going to work out. This algorithm applies DFS. So in the game tree, we have to go all the way through leaves to reach the terminal node. So DFS search, आप जानते हैं depth first search में क्या होता है? So we have to go to each and every node till it reaches to the destination. So that kind of a game tree is in this, and where the Minimax algorithm is going to work out. At the terminal node, the terminal values are given. So we will compare those values and backtrack the tree until the initial state occurs. So obviously from top to bottom, it goes from top to bottom, and then from bottom to top. So obviously the initial state will be there, and from the initial state, it will keep on continuing going to each and every node, and then it will go to the destination node. And while backtracking, it will go from destination node to the initial state node. So in this way, it will work out as a workout for the search techniques as far as Minimax algorithm is concerned. Now let us consider the example of a two-player game tree. Let us assume we are playing a game. There are two players in this game, and we will start operating how these two players are going to play as an opponent to each other. So how they are going to play. So with the help of example, always it is easier to understand. So you can see the tree diagram, which is also called as a game tree. So there you have A, B, C, D, E, F, G, H, I, J, K, L, M, N, O up till that. Then you have the terminal values are also there. So H is -1, I is 4, J is 2, K is 6, L is -3, M is -5, N is 0, and 7 is 0. Then the levels are also divided. So first level, you can see that there is a maximizer. The second level, there will be minimizer. Again, there will be maximizer, and the end, there will be a terminal node. So everything is between maximizer and minimizer. There will be an initial state which is at the maximizer, and then it will have a terminal node. Now, how this is going to work out? In the first step, the algorithm generates the entire game tree and apply the utility function to get the utility values for the terminal state. In the below tree diagram, let's take A as an initial state of the tree. Okay. Suppose maximizer take first turn, which has the worst case initial value as -infinity. So let us consider that the initial maximum value or the worst case initial value, ऐसे समझ के चलते हैं कि A की सबसे worst case value है, तो वो कितनी है? -infinity. And the minimizer will take a turn which has a worst case initial value as +infinity. So this maximizer is having the worst value because as it is a maximizer, it should have maximum +infinity, but the worst value about it is a -infinity. And the worst value for the minimizer will be +infinity, right? So we have considered the values. Now, step 2. In the step 2, we are going to find the utility values for the maximizer. Its initial value is -infinity. So we'll be having each value in the terminal state with initial value of maximizer, and determines the higher node of the values. It will find the maximum among all of them. ठीक है? So अभी initial value, अभी देखो इसका मैं आपको meaning समझाता हूँ कि how it does work. Now let us assume that there is a node D. So D will be having max -1 value. Okay. So it will be -1 to -infinity. Is it okay? It will be having -1 to infinity. Then it will be having max. So what will be the minus infinity? In this case, it will be -1 and it will be 4. So in this -1 and 4, what is the maximum value? 4. Now let us assume for node E. So E will be having 2. Again minus infinity. Worst case की value भी लिख रहे हम. This is the worst case values, right? We are in the maximizer. This D, E, F, G. We are into the maximizer. Maximizer की worst value कितनी है? minus infinity है. और उसकी value कितनी है? -1 है और 4 है. बराबर ना? D आगे नीचे गया तो टर्मिनल नोड पे उसकी वैल्यू -1 एंड 4 है. इसमें से मैक्सिमम वैल्यू क्या है? 4 मिल गई. अभी E की तरफ जाएंगे. In case of E, it will be having the second, बराबर 2 है और minus infinity. Worst case value 2 है and minus infinity. But the value is J and K, so that is 2 and 6. So in this maximum value is 6. Now for node F, so we'll go here. F will be having -3 and in minus infinity. When it will go down, that means -3 and -5. Obviously -3 और -5 में बड़ा कौन है? -3 है ना? -3 और -5 में -3 बड़ा है. So you'll get a -3 here. Now for node G, you will be having maximum 0 and minus infinity. Okay, so maximum will be 0 and 7. The highest value will be 7. This is the step number 2. In step number 1, we decided the worst case values. So the worst case value, as far as the maximizer is concerned, it is minus infinity, as well as minimizer is concerned, it is plus infinity. And then we had the terminal values, and accordingly the values will be selected. So from node D, E, F, and G, this is the maximizer level, and we are going to see the worst value, which is nothing but minus infinity. Is it okay? This is step number 2. Now step number 3. In the next step, it turns to the minimizer, right? Now it will be having the minimizer. So it will compare the node values with plus infinity. So now instead of minus infinity, it will be having the plus infinity. So now what will happen? Now will be the third layer node value. So यहां से देखोगे तो minimizer कितने लेवल पर है? थर्ड लेवल पर है. बराबर. अभी हम B और C की बात कर रहे हैं क्योंकि हम minimizer लेवल पे है. B और C में B is nothing but 4 and 6. So it is having the value as 4. क्योंकि मिनिमाइजर है तो इसमें से मिनिमम वैल्यू हमको लेनी पड़ेगी. सो 4 and 6 में से मिनिमम वैल्यू आ गई 4. अभी नोड सी जो कि दूसरा नोड है, नाउ व्हाट विल हैपन? इट विल हैव -3 and 7. सो व्हाट इज द मिनिमम वैल्यू? ऑब्वियसली -3. सो नाउ यू गॉट दिस 4 and -3. सो दिस इज द मिनिमाइजर लेवल, दिस इज द maximizer level, and this is the terminal node. So you have to remember the steps how it goes like. Now we are into the last step, again maximizer. We are into the last step. So now it's a turn to them for the maximizer, and it will again choose the maximum of all node values and find the maximum value for the root node. In this game tree, there are only four layers. So 1, 2, 3, and 4. Hence we reach immediately to the root node. But in real games, there are more than 4 layers. ये बहुत छोटा सा एग्जाम्पल है. इस एग्जाम्पल में इमीडिएटली आप पता लगा सकते हैं कि मैक्सिमम वैल्यू कितनी है, मिनिमम वैल्यू कितनी है. पर ऐसा हो सकता है कि बहुत ज्यादा लेयर्स होंगे क्योंकि गेम छोटा थोड़ी होता है, कॉम्प्लिकेटेड होता है काफी, और उसमें बहुत सारे लेयर्स होंगे. तो फिर ये करते समय द कॉम्प्लिकेशंस विल बी more as compared to these. This is a very simple example how this game approaches with the help of these nodes. So now what is happening? So 4 and -3 mein max will be 4 because we are again choosing maximizer. So now we have reached to the number A, that is called as 4. So that was the complete workflow of maximum 2-player game. Sorry. So This is how the two-player game works out. And this is how the Minimax algorithm works out. Now, let us see some of the properties of the Minimax algorithm. First is a complete. So this algorithm is a complete algorithm. It will definitely find a solution in a finite search tree. Obviously, solution ढूंढने की कोशिश वो करता है. Hence, it is called as the complete algorithm. It is also called as optimum because both the opponents are playing optimally. दोनों भी एक जैसी play कर रहे हैं. Time complexity, as it performs DFS, so which is nothing but depth first search. And so the time complexity of Minimax algorithm is O B raised to M. You remember this one. This is a very important line. It may be asked in the exam. So the time complexity of minimum algorithm is Minimax algorithm is O B raised to M, where B is a branching factor of the game tree and M is the maximum depth of the tree. Okay, so B is the branching factor and M is the maximum depth. Then it comes have a space complexity. So space complexity is also similar to DFS, which is nothing but OBM. Then we have limitations of Minimax algorithm. The main drawback of the Minimax algorithm is that it gets really slow for the complex games such as chess, Go, etc. So obviously, the drawback of this Minimax algorithm is that for the complex games, it will become slow. It becomes little slow. For example, you can say that chess or it may be Go games where it after a while it starts getting slow. These types of games have a huge branching factor, which is nothing but B, and the player has lots of choice to decide. So obviously choices बढ़ जाते हैं game के, तो बहुत सारे choices क्योंकि it is having a huge branching factor, and hence the choices will also increase. The limitations of the Minimax algorithm can be improved by alpha beta pruning. So there will be some drawbacks always for each and every algorithm which has been overcome by the next coming algorithm. So it has some good properties, has some limitations, few of the limitations, like it gets slow and always have a lot of choices to decide. And henceforth, in order to remove all these drawbacks, we go to the next algorithm called as alpha beta pruning. So alpha beta pruning is nothing but it is same like an alpha beta, but it is an improved version. Some kind of modifications is done in alpha in Minimax algorithm, and then came up with a new version. It's like a change modified version. So it is also an optimizer technique for the Minimax algorithm. उसको थोड़ा optimize किया है ना? वो गेम को थोड़ा ऑप्टिमाइज किया है, ऑप्टिमाइजेशंस करके एक नया एल्गोरिथम बनाया. As we have seen in Minimax search algorithm, the number of game states it has to examine are exponentially in depth of tree. है ना, देखा है. O B raised to M. So exponentially हो गया ना. Depth क्या है उसमें? M है. B क्या है? Branching factor है. So obviously the number of game states कितने हो गए? Suppose branching factor 2 है और डेप्थ 2 है, तो कितने लेयर हो गए? 4. करेक्ट ना? सो डेप्थ 2 है, ब्रांचिंग फैक्टर भी 2 है, सो 2 raised to 4 हो गया, यानी कि 2 raised to 2 हो गया, यानी कि 4. सो हाउ इट इज एक्सपोनेंशियल इन डेप्थ ऑफ अ ट्री. Since we cannot eliminate the exponent, but we can cut it to half. So exponentially कोई वैल्यू को तो हम एलिमिनेट नहीं कर सकते, मगर उसको हम हाफ रिड्यूस कर सकते. Hence there is a technique by which without checking each node of the game tree we can compute the correct minimax decision, and this technique is called as pruning. So actually in this technique what we are doing is that without checking each and every node of the game tree we can compute the correct minimax decision. इतना सारा करना है और करेक्ट डिसीजन पे भी पहुंचना है और इतने सारे नोड भी चेक करने हैं, तो पॉसिबल नहीं है। तो वो निकालने के लिए with the help of this technique, what it is possible is that without checking each and every node, we can compute or we can go for a correct decision. And this technique is called as pruning. This involves two threshold parameters. अभी इसमें दो parameters है, alpha beta for the future expansion, and hence it is called as alpha beta pruning or alpha beta algorithm. Alpha beta pruning can be applied at any depth of the tree, and sometimes it not only prune the tree leaves but also the entire subtree. So obviously the game tree is there, so it is having nodes, it is having leaves, it is having subtrees which is made up of subtrees will make it together as a tree. So it is not only applied to the depth of the tree, but it also applied to prune the tree leaves as well as the entire subtree. So each and every node, each and every subtree, so it can just be applied not only to the depth but also applied to the tree leaves as well as the entire subtree. The two parameters can be defined as one is alpha and beta. So जैसे minimax में क्या होता है, minimax में minimum value और maximizer value, minimizer और maximizer. So इसमें वापस वैसा ही है लेकिन modified version है, क्योंकि हम जो drawback है वो remove करने की कोशिश कर रहे हैं. तो फिर हमने क्या किया, दो चीजें निकाली, अल्फा और बीटा. So alpha is nothing but the highest value and beta is nothing but the lowest value. So the best highest value choice we have found so far at any point along with the path of maximizer. So that is the highest value of the alpha, and the initial value, you know, it is minus alpha, minus infinity, which we have already seen in minimax. So for max it is minus infinity, for minimum it is plus infinity. So similarly here there is an alpha, minus infinity, beta plus infinity. The alpha beta pruning to a standard minimax algorithm returns the same move to the standard algorithm does. So obviously the same kind of thing happens like which has happened in minimax algorithm, but it removes all the nodes which are not really affecting the final decision. वहां पर कैसा हर नोड पे जाना पड़ता है क्योंकि उसको पता है कि डिसीजन लेने में सारे नोड इंपॉर्टेंट है, मगर इस केस में हमने कुछ ऐसे टेक्निकल चेंजेस किए जिसके वजह से हर एक नोड पे जाने की जरूरत नहीं है. वो कैसे की है, यहाँ पर since we cannot eliminate the exponent but we can cut it to half, and hence there is a technique to which without checking each node of the game tree we can compute the minimax decision. So same thing की वजह से हर नोड की तरफ जाने की जरूरत नहीं है अल्फा बीटा में. जो काम के नोड्स है, जो डिसीजंस पे इफेक्ट करेंगे, बस उतने ही नोड को कंसिडर करना है और बाकी नोड को करना नहीं है, जिस वजह से एल्गोरिथम हमारा स्लो नहीं होगा, वो फास्ट होगा, है ना. सो बट इट रिमूव्स returns the same move to the standard algorithm, but it removes all the nodes which are not really affecting the final decision but making algorithm slow. So हर नोड पे जाने की जरूरत नहीं है क्योंकि वो स्लो कर रहा है. The better way is that go to the selected nodes only which are affecting the decisions, and hence by pruning these nodes it makes the algorithm fast. Now what is the condition for this alpha beta pruning? The condition is that alpha should be greater than or equal to beta. So alpha should be greater than or equal to beta. So what is alpha? It's minus infinity. What is beta? It is plus infinity, right? So it should be ranging between minus infinity to plus infinity. So this condition, when it follows, then we say that it is an alpha beta pruning. Key points of alpha beta pruning. The max player will only update the value of alpha, obviously, and the min player will update the value of beta. While backtracking the tree, the node values will pass to the upper node instead of values of alpha and beta. बराबर, मतलब बैक ट्रैकिंग के वक्त देखो ये वहां पर फर्क है उधर और इधर. While backtracking, they go to each and every node. But in this case, the node values will pass to the upper nodes instead of alpha and beta. We will pass the alpha, beta values to the child nodes. It will be better understood if we go with an example. Okay. Now let us take an example of a two-player search tree to understand the working of alpha beta pruning. So chalo step 1 lete hain. So at the first step, there is a maximum. Second step, minimum. Third stage, again a maximum. And then we have a terminal node. So at the first stage, the max player will start the first move from node A, where alpha is minus beta and beta is plus infinity. Alpha is minus infinity, plus is beta is plus infinity. These values of alpha and beta pass down to the node B. ये value B की तरफ जाएंगे, where again alpha is minus infinity and beta is plus infinity. And node B passes the same value to its child D. So this is the child D. बराबर, D and E. यहां से भी C से फिर गया child F और G को. Okay, so इस तरह से flow रहेगा. Now how it actually works out? Step number 2. Now let us assume that at node A, D is there. So the value of alpha will be calculated at its turn for max. So the value of alpha is compared with firstly 2, right? And then 3. The maximum of 2 and 3, यानी ये 2 और 3 में कौन सा मैक्सिमम है? 3 है, तो यहां पर आ गया 3. अभी यहां 3 आ गया, मतलब क्या हो गया? यहां 3 आ गया, राइट ना? यहां से 2 और 3 से यहां 3 चला गया. So will be the value of alpha at node D, and the node value will also be 3. So यहां पर 3 आ गया. Now step number 3, B पे 3 आ गया. Now B is beta with plus infinity. Will compare the available subsequent node, that is plus infinity, with the 3. So it will be 3. And hence node B is now minus infinity and beta 3. Is it okay now? Are you understanding? Okay. So hence B is now alpha equal to minus infinity and beta equal to 3. So from here we have started. So we compared 2 and 3. We got a 3. So यहाँ 3 मिल गया. अब 3 मिलने के बाद वो B की तरफ चला गया. अभी यहाँ जब 3 था तो उस वक्त मैक्सिमम था. जब मैक्सिमम था तो हमने इंफिनिटी लिया, बराबर. मैक्सिमम था तो इंफिनिटी लिया. जैसे वो इधर चला गया वो मिनिमाइजर में चला गया. सो मिनिमाइजर में चला गया तो इसका मतलब उसने 3 लिया, है ना? सो 3 लिया तो अब मिनिमाइजर की कंडीशन क्या है? माइनस इंफिनिटी है. सो इस स्टेज में कितना हो गया? बीटा 3 हो गया और अल्फा कितना हो गया? माइनस इंफिनिटी. अंडरस्टैंडिंग? नाउ स्टेप नंबर 4. नाउ एट ई नोड, अभी ये डी हो गया, बी भी हो गया, अभी ई की तरफ चलते हैं. The value of the alpha will change. The current value of the alpha will be compared with 5. Now यहाँ पर 3 आ गया, बराबर. So beta is 3. Now in this case what will happen? It will go to maximum. So 3 और 5 है ना? यहाँ 3 है, वो इधर आ गया E के पास. तो अभी यहाँ पर कितना हो गया? बीटा 3 हो गया और अभी मैक्सिमाइजर क्या हो गया? अल्फा है. अल्फा कितना हो गया? 5. Understanding? This 5 will come here. So alpha will be as 5. Now 5 और 3 में कौन बड़ा है? The alpha has to be greater than or beta, right? So this 5 will be greater than or equal to 3. Hence what will happen? This will have the value of 5. So यहाँ पर देखो अल्फा 5 है, बीटा 3 है, वो जो कि ऊपर से आया है. So the right successor of E will be pruned and the algorithm will not traverse it, and the value of the node E will be 5. So here you will get the 5. I hope you are understanding. Step number 5. Now the next step of the algorithm again backtrack the tree. Okay, so again we'll be having the node from node B to node A. So at node A, the value of alpha will change to maximum available value, that is 3. Okay, so in this case, it will be maximizer will be infinity and 3, which is nothing but 3, where beta is equal to plus infinity. These two values now pass to the right successor of A, that is node C. अभी यहां तक आ गए हम, यहां से 3 वैल्यू इधर चली गई. सो यहां से 3 वैल्यू इधर चली गई, मतलब अभी अल्फा 3 हो गया और बीटा आपका इंफिनिटी है. अभी यहां से वो जाएगा सी को. सो यहाँ मिनिमम है, सो मिनिमम के वक्त क्या हो जाएगा, अभी इधर अल्फा यहां से 3 इसको पास हो जाएगा, बराबर. अल्फा सक्सेसर है ना. सो एट नोड सी अल्फा विल बी इक्वल टू 3 and beta will be equal to infinity. Now what will happen, the same value will passed on to the f. So the same thing will be passed f to f. Now इस केस में f कितना हो गया, 3, बराबर. At node f the value of alpha will be compared to the left child, which is equal to 0. Okay, and maximum 3 and 0, so it will be 3. Then compared to the right child which is equal to 1. So ये 0 है यहाँ पर, तो ये 3 रहेगा, क्योंकि 3 और 0 में 3 बड़ा है, तो ये 3 रहेगा. लेकिन अभी इस दोनों में कंपेयर करेगा तो 3 और 1 में कंपेयर करने के बाद इट विल स्टिल रिमेन 3, है ना. देखो विच इज मैक्सिमम 3 and 0. सो इस केस में यहाँ पर 3 आ गई वैल्यू और यहाँ 0 है, तो ये 3 और 0 में कंपेयर करेगा तो नोड उसको क्या मिलेगा, देन कंपेयर टू द राइट चाइल्ड विच इज 1. सो maximum of 3 of 1 will be equal to 3. So alpha still remains 3, but node of value of f will be equal to 1. So f की वैल्यू तो 1 रहेगी, मगर अल्फा जो रहेगा वो कंपेयर करके 3 ही रहेगा. So alpha will be equal to 3, whereas the load value will be 1. क्यों, क्योंकि कंपेयर टू द राइट चाइल्ड विच इज इक्वल टू 1, सो ये 1 इधर चला जाता है. इज इट राइट? यहां हो गया आपका 1 और 3. नाउ स्टेप नंबर 7. नाउ नोड एफ रिटर्न्स द वैल्यू 1. यहां पर 1 है, अभी वो 1 सी को दे रहा है, बराबर. सो 1 इट एट सी. सो इस केस में क्या हो गया है, यहां से अल्फा 3 आ रहा है और बीटा यहां से 1 आ रहा है. सो इस केस में अल्फा 3 है और 1, बीटा इक्वल टू 1. अल्फा 3 है एंड बीटा इक्वल टू 1. Hence the value of beta will be changed, it will be compared with the 1. So minimum alpha and 1, बराबर ना, सॉरी इंफिनिटी एंड 1. सो ये दोनों कंपेयर होगा, क्योंकि इधर इंफिनिटी और 1 कंपेयर होगा, क्योंकि यहाँ पर वैल्यू आ गई. सो द नेक्स्ट चाइल्ड विल बी इक्वल टू सी. So now at C, alpha is equal to 3 and beta equal to 1. Again, it satisfies the condition alpha greater than beta. आ गया यहाँ पर alpha greater than beta. So the next child of the C, which is G, be pruned, and the algorithm will not compute the entire subtree G. So वो आगे जाएगा ही नहीं. Understanding? So इस तरह से वो C तक ही परफॉर्म करेगा, C to F ये वाला कंसिडर करेगा. In this case, what will happen is that कि जैसे वो satisfy करता है अल्फा is greater than or equal to b, वो आगे जाएगा नहीं. इस केस में भी देखोगे, इस ब्रांच में वो आगे गया ही नहीं, यहाँ पर ही वो satisfy हो गया कि कंडीशन अल्फा इज ग्रेटर देन बीटा आ गई. उस वक्त वो वहां पर उसने स्टॉप किया और ये उसने एग्जीक्यूट नहीं किया. सिमिलरली वो सी पर ही वहां पर आ गया और बाद में वो एग्जीक्यूट नहीं करेगा. दैट मीन्स व्हाट विल हैपन हियर इज दैट अल्फा इज इक्वल टू 3, दैट मीन्स अल्फा ग्रेटर देन और इक्वल टू बी हो गया, दैट इज 3 ग्रेटर देन इक्वल टू 1, and henceforth after that this G branch will not be executed. This is called as the working of alpha beta pruning. Now step number 8. Step number 8. C now returns the value of 1 to A. अभी A को उसने 1 की वैल्यू दे दिया. Here the best value of A will be 3, 1, which is equal to 3. So 3 है. Following is the final game tree which is showing the node which are computed and the nodes which has never computed. Hence the optimal value of the maximizer is 3 for this example. So यहाँ आने के बाद ये 3 वैल्यू ही रहेगी. देन यहाँ से 3 इधर गया, इधर 3 गया, इधर 3 गया. सो ये पूरा मैक्सिमम 3 वाला जो रूट है ये सर्च यहाँ पर कंप्लीट हो गई. दिख रहा है? दिस वन. This is how the execution of alpha beta pruning works out to be. Now, working of alpha beta pruning, there is one more concept that we are going to see, two types. The effectiveness of alpha beta pruning is highly dependent on the order in which the node is examined. So obviously, कौन सा node examine होता है कब, उस पे depend करेगा. Move order is an important aspect of alpha beta pruning. Now it can be of two types. The first is worst ordering and the second one is an ideal ordering. Obviously, when I said that the worst ordering and ideal ordering, so इसमें हमने क्या किया है पता है क्या? सिंपल सी बात है कि मिनिमैक्स एल्गोरिथम हर एक नोड चेक करता था, इस वजह से एल्गोरिथम स्लो हो जाता था. मगर यहाँ पे हमने क्या किया, द एक्सपोनेंशियल को हमने कट किया, हाफ किया. सो ओ बी रेस टू एम की जगह पे हमने किया ओ बी रेस टू एम बाई 2. सीधी सी बात. और वो हाफ करने की वजह से वो नोड्स नहीं ले रहा है जिसकी जरूरत नहीं है, जिसको इफेक्ट नहीं करेगा. सो हमने वहां पर देखा ना कि कुछ एक ब्रांचेस थी जो इफेक्ट नहीं कर रही थी बिल्कुल, और कुछ एक ब्रांचेस जो इफेक्ट कर रही थी, उसी ब्रांचेस को हमने ऑपरेट किया. एंड दैट इज व्हाट द अल्फा बीटा प्रूनिंग इज अबाउट. So now there are two ordering, because ordering of the node is very, very important. Otherwise, your algorithm will not work properly. So there are two types of ordering. One is a worst ordering and the second one is an ideal ordering. Worst ordering, in some cases, alpha beta pruning algorithm does not prove any leaves of the tree and work exactly as minimax algorithm. In this case, it also consumes more time because alpha beta factors such as move of pruning is called as worst ordering. In this case, the best move occurs on the right side of the tree and the time complexity is nothing but O b raised to m. Worst condition में क्या होगा कि alpha beta pruning बिल्कुल minimax algorithm की तरह काम करने लगेगा. That is the worst case. Simple सा logic है. Worst case में वो minimax algorithm जैसे काम करने लगेगा और जो टाइम कॉम्प्लेक्सिटी है वो बन जाएगी ओ बी रेस टू एम. बिल्कुल सेम, हर एक नोड देखेगा, चेक करेगा एंड देन इट विल एग्जीक्यूट. बट आइडियल ऑर्डरिंग में क्या होगा कि अल्फा बीटा प्रूनिंग विल हैव लॉट्स ऑफ प्रूनिंग हैपनिंग इन द ट्री एंड द बेस्ट मूव्स अकर्स टू द लेफ्ट साइड ऑफ द ट्री. वो लेफ्ट साइड से शुरू करेगा. We applied DFS, hence it's a first search left of the tree and go deep device. Obviously हमने बेस्ट फर्स्ट सर्च जो किया था, डेप्थ फर्स्ट सर्च, वो लेफ्ट से शुरू हो रहा था, बराबर. सो हर वक्त वो लेफ्ट से शुरू हो जाता था और एग्जीक्यूट करता था. So we applied DFS, hence it's a first search left of the tree and go deep twice as minimax algorithm in the same amount of time. The complexity in the ideal ordering will be O b raised to m by 2. So दो चीजें हैं जो आइडियल ऑर्डरिंग में बहुत इंपॉर्टेंट है. एक, ये वो लेफ्ट साइड से शुरू करेगा. दूसरा, वो कॉम्प्लेक्सिटी ऑर्डरिंग जो हो जाएगी वो ओ बी रेस टू एम बाई 2 हो जाएगी. And then we are moving to the last point of the alpha beta pruning and last point of this unit also. So there is nothing but rules to find good ordering. Now how you can select, that is the most important thing, because ordering कैसे चूज करना है ये बड़ा टिपिकल काम होता है. अगर ऑर्डरिंग गलत हो गई तो बिल्कुल मिनिमैक्स एल्गोरिथम की तरह काम करेगा, मगर अगर वो उसकी ऑर्डरिंग परफेक्ट हो गई तो वो बिल्कुल अल्फा बीटा प्रूनिंग की तरह काम करेगा, जिस वजह से एल्गोरिथम फास्ट हो जाएगा. सो देयर आर सम ऑफ द रूल्स टू फाइंड आउट द गुड ऑर्डरिंग. सो व्हाट आर दैट रूल्स? Following are some of the rules to find the good ordering in alpha beta. So these are the rules. The first one is occur the best move from the shallowest node. Second, order the nodes in the tree such a way that best nodes are checked first. Third, use domain knowledge while finding the best move such as chess, triorders, like capture first, then threads, then forward moves, backward moves. So उसको domain knowledge होना बहुत जरूरी है, वो अगर रहा तो अच्छा रहेगा. Best nodes find out करेगा, shallowest node find out करेगा, है ना? And then we can also bookkeep the states and the possibility that state may repeat. We also say that there will be states which will be repeated. So keep a note of that also, where the states will be repeated. So in these 4 steps, you can understand what is the good ordering of the alpha beta pruning. So here we end this unit number 2 as well as alpha beta pruning. So in the next lecture, we actually take a revision a little bit, and then we'll move to unit number 3.